Hey, welcome back. So I don't want to waste too much time doing little introductions of these videos. We can just pick up with where we left off. What we really had talked about so far was how the Earth is heated and how the Earth retains heat. A couple different ways. We talked about the atmosphere and things like that. And one of the things that we touched on was this notion that solar radiation from the sun hits the Earth. The Earth is a sphere. And because the Earth is a sphere, we get what we call differential heating. And we've actually kind of already seen this, that we have hot temperatures here, cold temperatures here, right? Everyone's hopefully kind of familiar with the idea that it's warm near the equator and it's cold in the poles. But that actually kind of brings us to the next kind of aspect where we're going to go with this, because thermodynamics, I know this isn't a physics class or anything like that, but thermodynamics, one of the things that it talks about is heat flow. And heat, like many things, will flow down gradient. And what we call down gradient means it will flow from an area that has a high value to an area that has a low value. And in this case, we've got heat here, high value heat here in the equatorial regions, and in the polar areas, we've got low value of heat. So if we've got, all along this belt, Earth's belt, if you thought about it that way, generally heat will flow from areas of high heat to areas of low heat. So this is really simple. It actually doesn't work like this because things are much more complicated. Well, there's really two things, fluids, that can move that heat around Earth. One of those is air. Air is, by the technical definition of a fluid, it's a fluid, but it's a gas. We don't need to pick that apart. But air can transfer heat around, and water, which is much more conventional fluid, can also transport heat around. So we're actually going to put the water off to the side for now. We're going to talk about how air can transfer this heat. But as I mentioned, there's going to be some complications. The general idea is moving from this area of concentrated heat, high value heat, to this area of essentially depleted heat, a place where there's not as much heat. We've got a lot of heat here, not a lot of heat here. How are we going to move it? We're going to talk about the air right now. So what you can imagine is, as heat here in the equator is absorbed, what does hot air do? It's really famous for this. Hot air rises, right? So here in the equatorial region, I'm going to use some arrows to model the air. Hot air actually air is heated, and it actually rises into the atmosphere. And it actually rises, and once it hits that density boundary at the end of the troposphere, it actually flattens out, and then that hot air begins to flow both to the north and the south. Generally, I'm going to focus on the northern hemisphere here just to make it easy. But as that air travels further and further and further north or south of the equator, it begins to cool off. And what does cold air do? It's the opposite. It sinks. So cold air sinks, forming this kind of pattern, this what we call a wind cell. And actually, what we start to see is that these patterns will develop where here, as cold air is falling in the next zone of wind cells. And so there are actually three main wind cells that we see on Earth, and those are the Hadley, the Ferrel, and the polar cells. I'm not going to write them out. You can figure it out. And those cells basically transfer heat rising from the equator, falling at about 30 degrees latitude. Another interesting thing to add to this is actually the amount of moisture that air carries. So hot air, warmer air, has the capacity to hold more moisture. So here at the equator, kind of thinking again about how air is related to moisture content, when that air is heated, it begins to rise up and through the atmosphere, and that causes it to expand, and it's also slowly cooling off. So air that's separating and cooling off has a lower ability to hold moisture, meaning as it's kind of expanded and cooled, it starts to drop moisture. And so this is generally an area of high precipitation right along the equator. Now, moving to the north and the south, as that air continues to move through the atmosphere and it's cooling and cooling and cooling, and it begins to fall back down to Earth, as it comes closer down to the surface of the Earth, the air gets compressed. And that compression of air, again, as it's also warming, increases its ability to hold moisture, but it doesn't have any moisture left, right? So these areas about 30 degrees north and south of the equator are actually known for being incredibly dry. Again, similar pattern continued when we get kind of farther north, 60 or also, negative 60 down in the southern hemisphere. We have another band where we generally see wetter weather. And so the way that I've drawn these with just these kind of cross-section view of how these wind currents work is great when we can think about, these big wind cells, kind of 3 to the north of the equator, 3 to the south of the equator, so 6 in total. Those are generally the kind of the cycles that wind is going through. But there's a problem, and the problem is Earth is not sitting still, right? Earth is spinning, and that causes these cells to get deflected. The next thing we're going to discuss is the complicated part that I was talking about, the fact that the Earth is rotating. Let's see, get my camera right here. And so I wanted to quickly, if we just look at the Earth from the North Pole, right? So looking down on the Earth like a bird's eye view from space or something like that. We know that the Earth is rotating west to east, again, in this kind of counterclockwise motion. But what I wanted to bring up is that not every part of the Earth is spinning at the same rate. And this is, again, it kind of dips back into physics, but it creates what we call the Coriolis effect. So if I have a spot here and a spot here, and we think about over the course of one day, right, the Earth spins entirely in 24 hours. And if we think about each of those spots, one of them covered far more distance in that same amount of allotted time, in that same 24 hours. So that the Earth is physically rotating faster near the equator than it is in the polar regions. And coming from geology, that also changes the shape of the Earth a little bit, right? The Earth is actually fatter at the equator and shorter from the North to South Pole. That aside. So what I wanted to highlight is the fact that this Earth, and as it's rotating, provides drag and kind of shears those winds. So as these wind cells are moving, I want us to take a second and think about the surface wind, right? So here in the Hadley cell, surface winds are blowing from about 30 degrees down to the equator. But again, the equator is moving more quickly. So what that causes is, if you were to think about how this wind will travel, that difference in speed actually causes these winds, rather than moving straight to the south, they actually shear. You get these curved lines that the winds travel in, kind of both in the north and south, right? So surface winds generally flow to the equator in that sense. And so on, if you kind of follow my diagram here. And these have actually been really important to us in human history, right? So if you imagine, again, just putting Europe over here and kind of North America over here, these winds have actually been what we call the trade winds historically, because the surface winds generally blow kind of from the European area to the Central America in the kind of equatorial region. The opposite is true as you go further north, so above about 30 degrees, those winds are generally carrying, winds are generally blowing to the northeast. And actually, that's one of the things that we had taken advantage of kind of in history back when we relied on wind for ocean transport.